Right. What is the objective? I already mentioned it. It's very clear. We want to solve more realistic problems. Problems where the area of the cross-section is actually changing and you don't assume that it's constant in each element. You can have forces or even material parameters that are changing continuously. Okay? We want to account for this. And in order to do that, we are going to introduce two concepts. Okay? Two concepts. The first one, you know it because it's something that you even do in surveying in year one. It's numerical integration, but we are going to revisit it and use it in the context of finite elements. And the second one, which is this word, isoparametric, what does it mean and how is it going to help us? Right? The structure, I'm going to use the same model problem. Then I'm going to introduce the concept of the reference element, which I think that you might know. And then this isoparametric transformation and the Jacobian. Okay, I'm putting in blue all the words that you actually need to remember and to know what they are. And then numerical integration, and then, as usual, with an example, everything is better understood. Right. So this is in one slide. My summary is partial differential equation or strong form, weak form or integral form, and system of equations. This is the path of the finite elements in a single picture. Okay? This is all you do in finite elements. And as I've been saying, we've done strong assumptions here. Okay? The other reason for what we are going to do today is you need to think that all of this is all very nice when you solve a problem of 3 elements by hand, but that's not the point. Okay? Solving a problem by hand helps you to understand the method. But in reality, we need to use computers to solve problems with millions or even billions of elements. Okay? So we need to program this. And to program it, something that we've done in the previous lecture, which is, where do I have it? Here, to have formulas for the shape functions that are dependent on the coordinates is not very clever. It's better to have the formulas defined for what is called an ideal or reference element. Okay? So the objective is twofold, but mainly we are thinking on computers. So what am I going to do? I'm going to select an ideal or reference element. I'm going to try to work everything out in this reference element, and then we will be able to compute the stiffness matrices for each element with a simple transformation. Right, so let's go here. First thing I'm doing then is introducing what I call a reference element. You need to think it as an ideal element. And I'm going to select it as -1 to 1. This is a choice, okay? It depends on the book that you go and check. Some people will use 0, 1 as an ideal element. Some people will use -1, 1. So it really depends on the taste of the author, if you like, that is right in the book. I prefer the -1, 1. It has some, in my opinion, some advantages, but it's not important. What do we do now in this reference element? Well, we know that in any element you have 2 shape functions. So in my reference element, I also have 2 shape functions, right? And what is the expression of them? We can build them exactly as we did before, because we have constructed already shape functions in the previous lecture. Right. First thing I'm going to do here. This reference element is an ideal element, as I said before. I want to insist. So the coordinates, I cannot call them x. X is my real life space. Okay? It's my bar from 0 to L. and the coordinate, I call it x, the horizontal coordinate. This is just an ideal reference element, and for that reason, to distinguish it, I'm going to use Greek letters here. Okay? All the books use the same letters, and they use chi for this one. And then when you see the shape functions as a function of chi rather than as a function of x, you instantly know that you're working in this referential element. Okay? It's another coordinate system, as simple as that. Seems that I'm saying something very complex, but it's not. The expression for the shape function. Again, I want the shape function to be 1 in one node, 0 on the other node. We've done this before. Expression, you got it there. What I could do is write it and convince you that is correct. Okay? How do I convince you that is correct? It's very simple, because if you do n1 of 1 is 0, and if n1 of minus 1 is 1. And this is what you need to verify. If you satisfy these two things, that's it, done. This is the one. Okay? And the same thing for n2. n2 of 1 is 1, n2 of minus 1 is 0, so that's a check, if you like. Quick check that these formulas are correct. Happy? Right, so that's all fine. And once we have the shape functions, we can obviously differentiate them. Remember that we compute derivatives simply because they appear on the stiffness. Okay? So this is minus 1/2, by the way, minus 1/2, and this one here is 1/2. Right? Okay. Now, what is beneficial of doing this is that when you program it, when you put this into a software, the expression of the shape functions is always the same. I'm only defining the shape functions for this ideal element. Correct? And that allows you to put a formula into your code that does not depend on the element where you are. That's one of the reasons. And you say, oh, very good. But what happens when I am here in my real world? Okay, I got my bar that goes from 0 to L, and I have a little element here with two coordinates, x1 and x2. Okay. You need a connection in between these two. A change of variables you need, right? A change of variables. And this arrow here is what we call the change of variables, or the mapping, and this one is called isoparametric mapping. Right? So when you see this word, isoparametric, that looks something very complicated, think on a change of variables. It's nothing but that. Okay? And how do we write it? Well, it's something that you give me a coordinate here, and it transforms this coordinate into x's. This is why I'm calling this a change of variables. Give me a coordinate on the referential one, and I'll give you a coordinate on the real world. And how do we write it? Let me first write it, and then we can think why it's got this expression here. This is exactly what you got here. Why this formula? Can you see it? Can you have some intuition? Rather than, I hate memorizing things, so this is why if we understand things, it's better. Why this expression? I'm using the same shape functions. Where do I point? Here. The same shape functions that, remember, I use them to approximate the solution. I'm also introduce them all of a sudden in this change of variables. Actually, this is why it's called ISO. Okay? ISO means the same. So I'm using the same shape functions to approximate the displacement and in the change of variables. Why this expression here? Does it make sense? Think what happens with this mapping, with this transformation or change of variables at this point. It takes this point and it transforms this point where? Where you would expect?
Onto a node.
And, sorry?
Onto a node.
Which one?
Physical node.
Yes. The first or the second?
The first one.
Yeah. So you expect this to go here, correct? And you expect this one to go to a second. And the midpoint, you expect it to go where? In the middle or shifted or I don't know. In the middle, isn't it? Right? Okay. So what you expect is this mapping to basically shrink or expand the elements linearly, right? Linearly because you expected the first point to go to the first, the last to go to the last, and the center to go to the center. So in your head, you are expecting something linear. That's what you're telling me. In other words, but this is what you're telling me. This is the motivation for using linear functions here to define this mapping. Okay? Because you expect something that behaves well, behaves linearly. It's not shifting things in a crazy manner. And you also expect x of minus 1 to be x1. You just told me. You expect this point to be transformed to this one in here. What happens with this formula that I just gave you? Well, I can do this and see what happens. What is n1 of minus 1? 1. What is n2 of minus 1? 0. Okay, there you go. This is what you wanted. Yeah? You wanted the first point to be transformed to the first point. Here you have it. And what about the second? Similar. What is now n1 of 1? It is 0. n1 of 2, sorry, n2 of 1 is a 1. So here you have it, x of 1. So it transforms really the first point to the first point. This is just a check, what I just did for you, to really appreciate where is this formula coming from. Okay. The thing is, this is our change of variables that we are going to be using. And what I can do here is simply introduce these expressions here, this one here, and the second shape function, I can put it here. Okay, they are just formulas. So if I do that, what I'm going to get is a lot of manipulation, but don't get lost with the manipulations, please. I mean, just keep in your head the idea of what we are doing. So far, I only introduced one concept, which is a referential space from minus 1 to 1, the shape functions there, and a change of variables. Think on that. All these algebra and all these formulas cannot distract you from where we are going. This is n1. This is n2. And then you can rearrange stuff to get the formula that you have on the slides. Okay. So that's my change of variables. And I can differentiate this thing. And the derivative is simply 1/2 of x2 minus x1, which is, if you remember, nothing but half of the length. Half of the length. Now I think that you engineers, should be the ones really coping well with this concept, because you can really think on this change of variables in a mathematical way or in an engineering way. And an engineering way is a deformation. Okay? You got your ideal element. You can think of this ideal element as your initial configuration, right? And you can think on the final element, this one here, x1, x2, the one on the bottom, x1, x2 here. You can think on this as the deformed configuration, and the change of variables as a displacement field, correct? Can you think like that? You got an initial bar that compresses or expands, and it transforms from -1 to 1 to x1 and x2. Yeah? Tell me yes. Otherwise I'll cry. But okay, this is a way to think, rather than thinking on the maths and all these formulas that I wrote here. Think like that. What is the Jacobian? Sorry? It's just a number here. It's one number. It's L divided by 2. Yeah, but I'm not worried about, I'm not trying to, I'm trying to get your engineering intuition here. If the change of variables, I'm asking you to see it as a displacement field that transforms, excuse me, that transforms the -1, 1 into x1, x2, and the Jacobian is the derivative of this, what is physically, from an engineering point of view, what is the meaning of a Jacobian in this scenario that I'm trying to set in your head? What is the derivative of the displacement? Sorry? Yes. Okay. It's like a strain, or, I mean, strain and stress at the end of the day are the same in a bar because it's only one number in the middle, which is the Young modulus. Okay? So when you look at these quantities, you have two options. Just go with the formulas, go blind. As you can imagine, I don't like that, because you don't understand things. You can replicate, but you don't understand. Or, in order to get a meaning, think in solids. Think like an engineer. And look at this guy as this change of variables as a deformation, and this Jacobian as a strain or a stress. Okay, you will understand it a bit better. Right. I'm going to stop in here because I'm not going to finish. Let's continue on Thursday.